So what the? Kena come up pun nak. The best interesting.
English 的模面，
Reflection.
因为我们没有 define 在 integer 上面，我们 define 在 real，在 net
Kat integer kami. Oh.
Yeah.
Okay.
Yeah.
Thank you.
Hello, testing. Okay, good morning, everyone. Let's start the lecture. Any question from previous tutorial or lecture? I did some correction to the week 10 tutorial solution. You should look at the new form here. So far, okay? Okay with the content? Next week, maybe we don't have quiz because I think we are not still have quiz that not discussed yet. So maybe we will combine the last two quiz together. Is it okay? We will combine the last two quiz. Yeah. And we should do the quiz 1 week before the semester, so that we can discuss the quiz. Right? If not, then we proceed to today's lecture. So last week we talked about the locality of graph, where you imagine yourself standing on the vertex, and then you look at who is your neighbor, who are connected to you using an edge, and then you check whether a graph is a bar path height or not, whether you can partition your vertexes into two groups without connecting them using edges, and then I mean you only can have edge connecting both disjoint subset of vertexes, which you call the bipartition, and then you do some simple set theory operation on graph, where you take the subgraph and you also take the union of graph. Okay. So this week we will try to work on the graph. Okay. So work through the edges and see what we can play with it. This week lecture might be a bit challenging or fast because there's few new concept we need to handle. So please bear with me. Okay. So first we will talk about path on the graph. Let's get a number n first. And the graph, an undirected graph. So in your mind, you should think of one undirected graph. So I'm going to define this path is the path of length n from a vertex u to v in G is a sequence of n edges. Okay. So that's that u1 up to en. Such that EI has endpoint xi plus 1 and x0 equals to u and x n plus 1 equals to v. Yeah. So what do I mean by this? So this means that, for example, if we got a graph like this, a graph, okay, and then we got the starting point u and v. Then we think of it as the path from u to v. And then we label the edges 1, 2, 3, 4, 5. Okay, what do I start with? Okay, I should start with I should start with I minus 1 to I, and then this one is correct. And this one is okay, some indexing. So a path from u to v, we can write as is sequence of path from e1, e2, e3, e4, e5, and e6. Okay. So far, okay. So you just walk on the edges. So similarly, we can if the graph is simple, we can just use the vertex to describe our path. Okay. We can denote path by vertex equal and 0 up to. Okay. So for example, in this case, we also can write x0, x1, x2, x3, x4, x5, and x6. Yeah. So it's clear from the picture that there's only one way to do it. So if there's a multiple edge, okay, then specifying the vertex is so let's say we got a different edge joining S5 and X6, right? So if I just specify the vertex, it's not enough to tell that whether I go through E5 or E6. But if it is simple, then it's okay. Simple meaning there's no multiple loop. No multiple edges. So simple is fine. So this one. Okay, the next one is circuit. So if your path start and end at the same point, the path is called a circuit. So a circuit usually has length greater than 0. Okay. So a loop is a circuit, but a circuit is not necessarily a loop. Remember what's a loop? A loop is a path that connects the same vertex. Okay. Okay, so this is a circuit. It's a path. Okay. So what's the length of what's the path of length 0? So path of length 0 is just the vertex. Sometimes in the text you will read that they use the word walk. So it's also a path. And in this case, the circuit will become a closed walk. Okay. So we have simple path. We also can define what a simple path is. Or sometimes we call it a trail. So a simple path is a path without multiple edges. Okay. So you don't repeat the edges. Repeat the different edges at the same two vertex. Okay. So far, okay. Path circuit. Okay. How you label the path. So one thing you can do is try to work out the definition. This definition for directed graph. Okay. So one thing I can tell you that is you only can compose edges with the same direction. Okay. If edges with different direction, you cannot compose. Okay. You cannot work this way and then work this way. Okay. You only can work with the same direction. This is for directed graph. Okay. So far, okay. Just some definition of path. Okay, next. So next we'll define a graph to be connected. Okay. So what does connected means to you? So the graph is called connected if you pick any pairs of vertices, you can join them with a path. Okay. So if there's a path between every pair of distinct vertices. Okay. Otherwise we will call it unconnected, disconnected. Right? Otherwise it is disconnected. Okay. So for example, the cycle graph is connected. Okay. So every 2 points you can have a path. Every 2 points you can have a path. Okay, so this is connected. Something that's not disconnected would be something like this. Okay. So this is not connected, right? Because if you pick this point and this point here, there's no way to connect them. Okay. So this is disconnected. Okay. About okay. Disconnected, connected. So in this case, we will call this connected component. Okay. So those are connected, we will call them connected component. So there are 3 of them here, and then there's one connected component. Okay. So what's a connected component in precise definition? So hey, yep. Why is the square connected? This one? This one? No, I mean this 3 thing is disconnected. Yeah, all together. Yeah, all together. Yeah. So maybe I should write. Okay. Yeah. Yeah, this 3 thing is disconnected, not the single one. Okay, so if they are disconnected, we can define what's the connected component. Okay, so a connected component, the graph, is a connected subgraph G that is not a proper subgraph of another connected subgraph. Okay, so you might think that this definition seems a bit tedious, but if you look closely, I can't say that this part is a connected component, right? Okay, because this is a proper subgraph of another connected subgraph. Okay, so this part is connected. This part is a proper subgraph of it. Okay, but we don't want this. We don't want to call this thing a connected component. We want to call the whole connected subgraph as the connected component. Okay, so that's why we have this extra condition here. Okay. So one theorem you can make is if the graph or undirected graph is connected, then there is a simple path between every pair of distinct vertex. Okay, so I won't prove this, but one thing you could think about is, if it is connected, then the definition tells you that there will be a path connecting them. Okay, so why is it a simple path? So this means there's no multiple edges. Okay, so yeah, so you should reduce the path into a simple path by using the connectedness of your graph. Okay. The proof is inside the textbook. Just some technicality you need to. Yeah. Yeah. Okay. Next. Yeah. So like this one here. This is one example in your textbook. So you got 3 connected components. This example here. Because you cannot join B to D, you cannot join D to C, or B to H, B to F, e.g. D to A. So similarly for D, then you can check for the other connected component. Okay. So far okay with the connectedness. Any question? Yep. Oh, okay. You mean this part here? So okay, first of all, connected component is a graph that is a connected subgraph. Okay. So let's say we take this as an example, right? So what are the connected subgraph here? So maybe you also can take this as a subgraph, right? You also can take this connectedness, this as a subgraph, or this as a subgraph, or this one also as a subgraph. Okay, but the the um the condition here is you need to throw away all the proper subgraph of another connected subgraph. Okay, so these 3 themselves are connected already. Okay, and then this one is a proper subgraph of the connected. So we don't like this one, we don't like this one, we don't like this one, we don't like this. We only like this. We only like the whole connected sub. Okay, so these are the only 3 that survive. Okay, yeah, because yeah, okay, just some okay, yeah, this is the connected subgraph. Okay, the next part is Euler path. Well, what's the Euler path? Okay, so there's all time of this pound of Tony Birch. The mayor asked a question to Euler. If there's a way to start from the town and then passes the bridge once. Every bridge, there's 7 bridges here. Yeah. Is there a circuit that can pass through every bridge once? Yeah. Why? How do you know? Huh? What? I don't hear. From the internet, okay. Yeah. So yeah, so like some of you might know there's no way to do it. You can't pass through every bridge once and then come back to the town. Because this town connect three lanes and then become an important trading center. Okay, so what's the idea of this question? Why? So it's solved by Euler, so that's why we call it the Euler path. And we'll deal with Hamilton path later. So what's an Euler path precisely? We'll define two Euler circuit and Euler path. So an Euler circuit in a graph G is a simple circuit containing every edge of G exactly once. Okay. And then Euler path is just a path, but also contain every edge exactly once. So path you don't need to end and start with a same point, but circuit you need to start and end with a same point. Okay, so try for 2 minutes and then try if you can find some Euler path or Euler circuit in figure 1 or figure 4, for example. Try for 2 minutes if you can find any. So you can only allow yourself to use every edges once. Mhm. Okay. Any try on G1? Is there any Euler circuit or Euler path you can find? Anyone done? Try? Anyone try? Anyone try to do? Ah, sleeping. Everyone is sleeping. Anyone try? Euler path or Euler circuit? Hmm? Anyone manage to get it? Yeah? Okay. Try. Masuma. No? What? What have you done? Have you tried? Yes? Did you get anything? Okay, what did you get? For G1? The 8. So start from which vertex? A, middle point, E. Okay. And then which vertex you want to go to? E to A, and then A to B, E to E again, and then go to D. Okay, sure. So there's one way to go. C, there's one way to go. Okay. So this is the Euler circuit. How about G2? G2, you can try that there's no Euler circuit of path. Okay. And you can figure out a general argument saying why there's no Euler circuit of path. Okay. How about G3? Yes. What do you have? What do you have? B to E. Start from B and then to E. Okay. Go to D. E. A. D again. D. A. Okay. So this is an Euler path because this doesn't start and end at the M. I think there's no Euler path for this question. I mean Euler circuit. Yeah, there's only Euler path here. Okay. How about H1? So H1 you only can compose with the same direction. And then you can see that this one has a no Euler circuit of path. Okay. Because the direction is not the same, so you cannot close up the circuit or walk the path. How about H2? H2 should be pretty obvious. You can see that all the edges are flowing in the same direction. Okay, so you just follow the direction and then walk. There's only one way you can walk through this. Okay. So no matter where you start, you will end in the same point. There's only one way to walk around this. How about H3? How about H3? Do you have Euler path or Euler circuit path? Okay. So where should you start? C. I think there's only one way to do it. You can only start from C. If you don't start from C, then you will let out some of the vertex. Okay. So this one Euler. Okay. This is a Euler. Okay. Oh, good. So how to determine whether you have an Euler circuit or not? Okay. Then start we got a theorem. So to see that whether a multi-graph with at least two vertexes has an Euler circuit if and only if each of 8 vertexes have even degree. Okay. So you just need to make sure that every vertexes you got an even degree, then you got an Euler circuit. Okay. So proof. So there's two directions here. One direction is you have an Euler circuit. You want to show that the vertex all have even degree. Two is if you know that the vertexes are all even, then you can construct an Euler circuit. So one direction is easier. So start with an Euler circuit. You show that every vertexes have even degree. This is easier. Okay. So I just describe using a diagram, for example. Okay. So you got an Euler circuit, right? So let's say A is your starting vertex. Starting vertex A. So your path starts here. So that means you got a +1 degree to the vertex. And then you keep going. Yeah, you keep going, keep going, keep going. Okay. Whenever you passes a vertex,
it will become a +2 because you need to go in and go out, right? Go into the vertex and then go out the vertex. Okay. So in the meantime, you might pass back A again. Okay, but that's fine. You are still adding 2 to the vertex. Okay, and then you keep going, keep going. Every point you passes through, you will have a +2 to the vertex. Okay, so you keep going, and then because this is a circuit, so this means you have to finally come back to your starting edge. Okay, so you have to finally come back to the starting edge, and then you pass another 1 to the starting and ending vertex. So +1 become a +2. And every time you passes through a vertex is +2. So that means every vertex will have degree even. Okay. Is everyone following? So far, okay? Still following? Okay. So this is the first part. Okay. So second part is harder. So what we do is the first step you need to establish is whenever the vertexes, all the vertexes have even degree, then you can always form a circuit. Okay, you can always form a circuit if all the vertex have even degree. Why? Why? Actually, you also need connectedness. Or then you can together with the connectedness of the graph. Can you think of one? You can form a circuit with even degree vertex. Huh? Not possible for all. If you cannot find us. Yeah, okay. So because circuit, you need to return to the same vertex. So if you have even degree, then you have a path to connect back to your start or even start and ending vertex. Okay. But let me give you some examples. So because it's even, this means you can have a chance to go back to your starting vertex. So let's say, for example, you do the vertex, do the circuit. Okay, this is your graph, and then do a circuit. If you come back to the same point, okay, and use up all the edges once, then this is an Euler circuit, then you are done. But maybe you can work the other way. So maybe you work from this way. Okay, you also form a circuit, but it is not an Euler circuit. Euler circuit. Okay. However, you also can form, if you look at the subgraph, removing this circuit here, and then you will find that you left with this bit here. Or you got a circuit here. You got a circuit here. But the subgraph you're looking at, you also can form a circuit, right? Because it's still an even degree. Okay? Because even minus even, still even. And moreover, the graph is still connected. Okay? So you can form another circuit. So if you form another circuit, these two circuits joined together will form this Euler circuit. Okay, so you can keep repeating this process. So you keep finding circuit on your connected graph, and then you can join this circuit together to form the Euler circuit. Don't believe me. Don't believe, cannot see, don't believe this example. You see this, the green one is the combination of this square and the triangle. Yeah. Okay. Is it okay? Any question? No? You believe me or not? I mean, if you want to see the whole argument, you can go to the textbook. But I'm telling you the idea of the proof. Yeah. Okay. Yeah. Okay. Maybe I show you this example here. Much task. Okay. So I give you this graph here. So the claim is there's an Euler circuit here. So how you figure out the Euler circuit? There's like 1, 2, 3, 4, 5, 6, 7, 8, 17 edges here. So how you join 17 edges? Every edges exactly once. I think 18, 17, 18. Okay. So anyone know what's the Schema class is? What's Schema class? Yep. So yeah, so yeah, very good. So so is the banded sword. Yeah, let me show you the here first. Yeah. So can you find this diagram inside your graph just now? The graph just now. Find these two Schema types. Yeah. Can you find it in the graph? Okay, let me show you. It's in the textbook. So let me show you. So you can start from A, okay, to B, and then go to C, and then go up to E, and then go back from E, go back to F, E, and A. Okay. And then the other direction is you go from K, and then walk through G, F, D, and then walk back to G, walk to H, then walk to J, and then walk to okay. So if you join these two circuits together, you will get the Euler circuit. Okay. So this is like the two bending sword. Yeah. Two moon. How to draw two moon? Have you done it? Huh? Follow the moon shape. How? Like this, like this, like this. Like this. Oh, wait. Let me see what you're talking about. Okay, copy this again. Okay, so you say like these two moon, huh? Two moon. I think can. But this two moon, what's wrong with this two moon? This two moon didn't. Let me see first. I think this two moon didn't how to say, didn't follow the construction of the proof. Okay, because you know why? Because you cannot follow these two moon and then go to the other moon. You need to go out the other moon first, and then you get what I mean. So for this Shimata, right, you can finish one. Can I? Can I keep going? Can I? Huh? Cannot, right? Oh, say cannot. Never mind. Okay. Yeah. Okay. I think moon also can. Moon also can. Yeah. Moon also can. Okay. Then what do you mean? You mean this one, huh? I think because of the history. Yeah. Ah, right. Yeah, yeah. Because at that time they are like every day using this stuff. Then don't look at the moon. I don't know. Yeah, yeah. So it's just some history. Yeah. Okay. Okay. So we come back to the seven bridge problem, the convert now. Okay. So we got a land. We got a land here. Okay. And then we got three pieces of inlane, one island and three pieces of inlane. And then we connect the town with seven bridges. Okay, so the question is, can we pass through all the bridges exactly once? Yeah. So we also can write label the region A, B, C, D. Okay. And then reduce this connected component into one dot. E. Okay. And then we have two bridge connecting A and B. Okay, let me label it first. And then two bridge connecting B and C. And then one bridge connecting C and D. And then one bridge connecting A and D. And then one bridge connecting B and D. So we can turn this map into the graph. So is there any Euler circuit? So why? Using the theorem. Yeah, the degree is not even. So the degree of A, B, C is 3, and D is 3. Okay. And then degree of B, A. Okay. A, C, D is 3, and degree of B is 5. Okay. So they are all odd. At least one odd is enough, but all of them are odd. So then by theorem before Euler circuit doesn't exist in the graph. Okay. Yeah. So, but anyway, so Euler showed this to the mayor. But what happened to the place is that there's a war happening in the place. So all the seven bridges are destroyed. So get replaced by these three bridges. Okay, this is what happened to the town in the end. I think before that it belonged to Germany, but after the war it becomes Russia. Yeah. Okay, let's stop here. If any question you can ask. Otherwise, we will take a break until 10 o'clock.
Actually, what's the difference with circuit and path?
Oh, circuit just N and circuit. Yes. Okay. If a path begins and ends with a certain place, it's a circuit. So you can just come back.
So path just only
And end and start and end with different vertex.
Can tell me the difference of passes and simple passes? Can give me an example?
Example path and simple path.
一开始讲的，
Yeah.
对很多定义我都没有。
OK. 先让我确认一下哦。我确认一下。我去找一下，我告诉你，我应该等一下会告诉他们。看一下，我做一个最后确认才可以。这个比较好。写错。等一下我解释。等一下我解释。
可以
，OK，
我就看一下。
OK，
反正我下个也没。
我觉得这个写这个表，我觉得你先写这个也是很奇怪。你们看的。哪里？哦，对，OK，这样 OK，这样可以。因为这个，我就是看到这个很奇怪。哦，明白。明白。OK，明白。
我不太明白。
你不太明白哈？等下我写什么？OK，让我明白。
Result is
OK，他的意思是说，你不可以，给他的 idea 是这样，比如说你从这里去这里，如果你从这里跑到这里，再跑到这里，这个只是跑，这个是 simple，这个是不 simple。因为你看啊，你走过这里，你又重复了这条线。OK，
是这样。
就这样。
那你好。
不可以 repeat。我刚才用错字啊，用到 multiple。
那就好理解多了。
然后我再解释一下。OK，没有解释一下。
嗯，但是两个少。哦，跟你聊没有关系，我和你说，对没有我和你说，我和你说。
Pause this.
Okay, just now I talked about the simple path, right? I think I used some wrong terminology, so a bit confusing. So a simple path is a trail with is a path without repeating edges, okay, not multiple edges. So for example here, okay, example. So if you want to walk from U to B, okay, so one way to walk, there's a second way to walk. One way is you walk and then you turn a big round and then back, okay. And then one is you just walk straight, okay. If you walk straight, this is simple. If you turn around, it's not simple because this edge get repeated. Okay. And then this is precisely how you show that every connected graph has a simple path that connect 2 points. Okay. So if you do this big round here, you can actually throw away this bit here and then replace by this simple path. Okay. This is how you show that every two vertices in the connected graph can be connected by a simple path. Okay. Yeah. So this one not simple, without repeating. It is not multiple, just repeating. Okay. Multiple edges just capture edge between two vertex, but repeating edges will capture the long loop, long circuit. Okay. Okay. Any question? Okay, next we'll talk about Euler path. Okay. So how to form an Euler path? So you can check that connected multigraph has an Euler path, but not an Euler circuit. Okay, so because Euler circuit is also an Euler path, because Euler path just that Euler path doesn't require the starting point and end point is the same. But now let's say the starting point and the end point is different. Okay, so it's not an Euler circuit. Then it has exactly two vertices with odd degree. Okay, and if there are exactly two vertices of odd degree in the graph, then you can find an Euler path. Okay. So what are these two vertices of odd degree? These are precisely the starting and the ending vertex of your Euler path. Okay. So one way is easier. So if you got an Euler path, okay, then it implies that there's exactly two odd degree vertexes. Okay. So what are the two odd degree vertexes? Is the starting vertex and the ending vertex. Because you got a +1 contribution from the top and +1 from the contribution. Okay, all the middle one when you pass through them, you have to +2. Okay. Similarly, you can like come back to here, but that's fine. +2 +3 is still even, still odd. Okay. So every time the path passes through, you have a +2 contribution. But the starting vertex and ending vertex will have an extra +1. Okay, that's how you get the odd degree. Is everyone following? Following? Okay. How about the other direction? Okay. So if I tell you that there's exactly two vertexes of odd degree, so this should be your starting and ending part of your Euler path. So how you come up with the real Euler path? Like how you make sure that the path is Euler? Huh? So this question is harder, but there's one clever way to do it. which is using the previous theorem. You think of one. So you start with exactly 2 vertices of odd degree, the rest are even, and then you want to build an Euler path. Any idea? Yes, yeah. Sorry, say again. Connect the start and the end. Yeah. Okay, good. So let's say okay, so what do you mean by start at the end? So suppose U V are the 2 vertices of odd degree. Okay. Oh, let me. Okay. Then consider a larger graph. Graph by adding an extra UVH. Okay. Extra H UV. Okay. So every vertex will have even degree. Okay. So you got a U and maybe go somewhere to V and passes through some vertex. And then you do an extra connection. Okay. So you add a +1 to the odd degree. So everyone will have a even degree. So by theorem before, this larger graph will have an Euler circuit. Okay. So how to obtain the Euler path from Euler circuit? How to obtain an Euler path from Euler circuit? Huh? Yeah, so you just remove the extra hash again. So removing UV, you will get the Euler path. Because Euler circuit already help you to make sure that you will pass through every edges once. Okay. Then you just remove the extra edges, and you get the path. Understand? Understand? 单镜啊，单镜，你有单镜，单周，哎，倒镜，倒镜，倒镜，yeah. Why you look confused? Okay. Confused even. Huh? Yeah, I'm just confused. Okay. Wait. Okay. Euler path from Euler circuit. Still flowing. Okay. Good with all good with this one. Okay, next. So next, okay. Next we will deal with Hamilton path. So what's the Hamilton path? A simple path that passes through every vertex once. Okay. Just now we passes through every edges once, right? Now we passes through every vertex once. Okay. Exactly once. Is called the Hamilton path. Similarly, you can define for Hamilton circuit. So you pass through every vertex exactly once, other than the starting and ending vertex. Can I say other than? Oh no. Also include the similarly you can similarly for Hamilton circuit. So you start and end at the same point, it's a circuit, and then if you don't start and end with the same point, it's a path. So you have to pass through the vertex exactly once. So why is it called a Hamilton path? Because so Hamilton got this quest. He want to visit 20 cities in the world, and then these 20 cities have a connection between them, which he formed this dodecahedron. Yeah, dodecahedron. So I think there are 20 vertexes here, if I'm not wrong. But when he want to go around these cities, he doesn't want to revisit the cities. Okay, he just want to go to one city once, don't want to revisit it. So he asked a question whether he can do it or not. Okay, so he put it, draw a dodecahedron using the vertexes, using the city as the vertexes. Okay, so these are cities. Okay, and if you smash this dodecahedron, okay, you smash this polyhedron flat. Okay, smash it flat, and then you can get this graph here. Can you see it? So imagine you got this hexagon here, and then put it here, and then you can look around how many hexagon beside it. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Okay. So you smash it flat. Okay. It's like you step on the tin, aluminum tin. Right. So smash it flat. And then you can see that how many faces do you have here? You know, how many faces? Can you count? 12, right? So how many faces here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So where's the 12th one? Huh? So where's the 12th face? The number 12 face. Huh? Yeah, at the bottom, correct. So at the bottom. Okay. Yeah. Okay. At the bottom, meaning the largest hexagon here. You can like pull it. When you pull it out, you can see it. It's at the back. Okay. So put into the graph. So can you walk a path that passes through every vertexes? Not like this, cannot. But he provide the answer is like this. Okay, so you can do it. Passes through every vertex once. This is called a Hamilton circuit because it end and start at the same. So let's try some example here. Can you find some Hamilton path or circuit in G1, G2, and G3? I'll let you try for about 2 minutes. Try find some Hamilton path or circuit. If you got it, you can just focus. You got it already? Got it? Got it? E1, what do you have? Huh? You start from A, and then go to B, 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 A. So this one is a circuit and passes through every vertex one. So you got a Hamilton circuit. Do you have Hamilton path here? Yes. So what can you do? What can you do? A, B, E, D, C. Okay, so Hamilton. Okay, how about G2? What do you have? Do you have a Hamilton circuit or path? Path. So how do you draw the path? A, B, D, D. So this is a Hamilton path. And then you realize that there's no Hamilton circuit because whatever circuit you draw, you need to pass through AB twice. Okay, so you cannot avoid passing through the AB twice. So you will always meet. You will always meet A twice. Okay, A or B twice. How about G3? G3. So G3 has no Hamilton circuit or path. Okay. Similar argument with there's no Hamilton circuit in G2. So it's the problem of these three lines here. Okay. So no matter what you draw, path or circuit, you have to pass through either of them twice. Okay. Or path containing every vertexes must pass through AB, AB, DC, EF, or EF, or B. Oh, okay. Oh, EF. Okay, you can try it. No matter how you draw, you need to pass either one of them twice. Okay. So what are the conditions? What are the necessary or sufficient conditions for the existence of Hamilton path, Hamilton circuit? Okay. So it turns out that there's no easy condition to check. Okay. However, we can deduce some properties out of the Hamilton circuit. For example, a graph with vertex of degree 1, cannot have a Hamilton circuit. Okay, can you think of why? In and out. Yeah, in and out. So you cannot go back to this vertex again. So you cannot form a circuit. I think this is also true for any circuit. Okay. True for any circuit. So I don't need to write out. I will write it in my lecture note. But if a vertex in the graph only has 2 degrees, okay, then all the edges need to be used, right? Because you need to go in and go out. Then both edge must be part of any Hamilton circuit. Okay. If the vertex only have degree 2, the 2 edge must be used up in any Hamilton circuit because you need to pass through the vertex, right? Passes every vertex exactly once. Okay. And then the last one is when you construct a Hamilton circuit, if the vertex has more than 2 degrees, okay, passing through and vertex, passing through a vertex, then all other remaining edges incident to the vertex, incident with the vertex, can be removed from the consideration. How to write? Can be removed from consideration. So what do I mean by that? So let's see this example. Just now we construct a Hamilton circuit here, right? Okay. But B have degree 3, right? B have degree 3. So what it means here is, once I use up these two lengths, these two edges, I don't need to care about these edges anymore, right? Because if I want to come back to these edges, I need to meet B again, which I don't want. I only want to meet every vertex exactly once. Okay. So when you use up the two edges on the vertex, all the other vertex, all the other edges you don't need to consider anymore. Okay. Otherwise, you will need to come back again and meet B if you use the other edges. Got it? Okay. Oh, good. Okay. Okay. Next. So what's next? Okay. So next is look at this figure 11 here. So why are they don't have an Hamilton circuit? Okay. The first one, if the degree is you have a vertex of degree 1, you will never have a Hamilton circuit. Okay. Because this one is of degree 1. Why? Because you cannot come back to E again. Okay. If you want to come back to E again, then you need to meet D twice. Okay. How about H? Okay. So A, B, D, E got degree 2. Okay, degree 2 vertex. So you need to use up all these edges. Okay. So if you use up these edges, you will realize that you need to pass through C twice. Okay. So there's no Hamilton circuit here. So because you passes through C twice. Okay. Okay, following. Then we continue. So for example, the cycle graph or the complete graph, there you can find a Hamilton circuit on K3. K2 has no Hamilton circuit, but got a Hamilton path because you cannot come back to the original vertex. And then K4 got a Hamilton path. K5 also got a Hamilton path. But K5 got Hamilton path that is different from the cycle. Okay, you can do the stars. Right? You can do these stars. Hamilton. Path. Okay. K5 a bit different. And then this one. Maybe you can also find a non-trivial one, but not nice. Okay. Cycle all have a Hamilton path, which is this the outer one. Okay. So far, following. Okay, next. Next, they developed some theorem. Okay. The first theorem is all by all. So they check for degree that are not adjacent, a degree for vertex that are not adjacent to each other, and take the sum and compare it with the number of vertex. So let's say you got a graph with vertex more than 3. Okay. And if you compute non-adjacent vertex, degree of non-adjacent vertex, and then you add them out, it is greater or equal to n, okay, for every non-adjacent pair of vertex. So that means there's no path joining them. Then G has a Hamilton circuit. Okay. So from the idea just now, right? As long as you got enough edges to avoid meeting C again, then you can form the Hamilton circuit. This is the idea. So you need to make sure your degree is large enough. Okay, so this is the idea. How large is it? So all tells you that if you add up any pairs, okay, of non-adjacent vertexes and greater or equal to the number of vertex, you can find a Hamilton circuit. Okay. And then this one maybe seems a bit tedious. So we got another corollary by Dirac. So what Dirac do is you just need to check the degree of every vertex is enough. Okay. Instead of doing the summation. So the condition is you need to make sure that the degree of all the vertexes is at least n/2. Okay. As long as you make sure that the degree of your vertexes is more than n/2, then you can find a Hamilton circuit. Yep. Say again. Oh, if n is 5, and then the degree is 3. You need 3. You need ceiling. Yeah. You need ceiling. Yeah. Because right. You need ceiling. Yeah. And G, if you like, you can like this ceiling. That's the Hamilton. So you might wonder that whether the converse is true or not. So if you have a Hamilton circuit, is it true that every vertex have to be at least n/2? Or if G has a Hamilton circuit, is it true that every pair you need to more than n? Then you can find the Hamilton circuit. Actually, it turns out no. Okay. So it turns out no. So there's one simple example, which is the cycle of 5. Cycle of 5. For this hexagon here. So hexagon here, just now we already said that every cycle got a Hamilton circuit. Okay. But if you add up any two non-adjacent vertex, the degree of non-adjacent vertex, you get 2 plus 2, which is 4. Okay. But the number of vertex is 5, which is less than the number of vertex. Okay. So you got a Hamilton circuit, but the hypothesis is I mean this proposition here is wrong. Okay. So the converse false theorem is not true. It's false. Okay. Similarly, you can verify that using the same example, the converse of theorem is 4, because degree of every vertex here is 2, which is less than 5/2. So what does this tell you? What does this tell you? This tells you that if you can make sure your degree is big enough, then you can find a Hamilton circuit. But the condition you found is not the optimal one. Okay. You could have smaller degree, but you still can find the Hamilton circuit. So that means there's some other condition that's governing how you find the Hamilton circuit. Okay. I think there's something to do with the structure of your graph. So degree of the so why we are interested if and only why we are interested in the statement of if and only if, because if and only if can capture the result using different method. Okay, so if you can't produce an if and only if statement, that means you haven't captured enough information to get the result what you want. Okay. So what I think is there should be something to do with the structure of the graph. Okay, not just how many degree, how many line you can draw, but also how you connect the graph. Yeah. So if you can find that, then I think you can find the if and only if result. So degree itself is not enough to describe if you can find the Hamilton or circuit. Circuit. Yeah. Okay. So next part. So just now we deal with path. Now we come back to graph again. So this part we will deal with one type of graph called the planar graph. So one way to understand this planar graph is, let's say you got 3 houses. Okay, you got 3 houses. You want to connect them with different utilities. Okay. And you are living in a 2D world, for example. Okay. And then if you connect the gas pipe, the water tube, and then the electricity cable. Let's say what happens if you intersect the gas tube with water tube. Okay. Or if you intersect the water pipe with a electricity cable. Okay. So maybe you will cause some explosion, right? Okay. So you try to avoid this. But in our world, this is okay, because we are living in a 3D world. So if you are living in a 3D world, you can just leave the intersection away. Yeah. Okay. So in this topic here, we want to deal with 2D world. So planar graph we will talk about here is a graph is called planar if it can be drawn in the plane without any edges crossing. Okay. So planar graph we only deal with graph that has no edges crossing. And then such drawing we will call it a planar representation of the graph. Planar representation. So let's see an example, okay? Check this example again. So we got a complete graph K4 here. So it is 4 vertices with all of them connected by an edges or the vertex. So the question is this planar? Is this planar? Huh? What, not yet? It planar or not? Yes or no? Why it's not yet? Suddenly can yes, suddenly can no, right? Yes or no? Not obvious. So yes or no? Yes, okay, so it's yes. So it's a planar graph. So why is it a planar graph? But you got an edge crossing, right? Okay. But remember the isomorphism of graph? So we can redraw this graph without crossing. Okay. So we can leave the graph outside. Leave one of the edges to the outside. Okay. Just make sure that the edge that connected before is connected afterward. Okay. This is the isomorphism that last time we talked about. And then it is planar because it admits a planar representation. So that means you can draw. Oh, I keep repeating this. So that means you can draw a version of the graph such that there's no edge crossing. Okay, so this is called a planar representation of the graph. Okay, so far so good. Okay. Okay. Okay, the next example is this cube here. So you can see that this cube also have intersection, right? Non-trivial intersection. Okay, but is this graph planar? Yes. Okay, so similarly you can smash it one way. Okay, make it flat like this. And then once you see this, there's no intersection between the edges. So this is a planar representation of your cube. Okay. Similarly with the dotted cahedron, right? Just now we saw it. The Voyage problem, the Hamilton problem. It's also a planar graph. Okay. I think most polyhedron are planar graph. Polyhedron. You know what's a polyhedron? So like you can, for example, you can take a triangle and then you build the what do you call this? Yeah, we just call it a polyhedron. So it's like 3D of a triangle. Like the cube we build using the square. Okay, you also can build using the hexagon. You just stack a few hexagons together. Okay. So these are the polyhedron. Okay, next one is K33. So the complete bipartite graph of 3 vertex to 3 vertex. So what's the K33? So you split into a bipartition of 3 vertex, and then you join all the vertex across. Join all the vertex across. So is this bipartite? Sorry, is this bipartite? This is bipartite. But is this planar? Huh? Is this planar? No. This is not planar, but how on earth you're gonna show this is not planar? Okay. So one way to do it is I take this vertex, okay, and then I move it down. And what do I mean by that? So I draw it like this, and then I move it down where you get this picture here, reducing the intersection. Okay, can see it or not? I take this and then move it up. Okay. And then we still left with this vertex here. Okay. So if we want to reduce furthermore this intersection, edge crossing, we can see that there are few places I can put this vertex, R1, R2, and R3. Okay, so that's me either I put it outside here or I put it into this region. Okay, so if I still put it in outside region, okay, you can see that there's 1, 2, 3, at least, I think at least, yeah, at least 3 intersection, at least 3 crossing. Okay, so it's not ideal to put outside, but maybe we can put inside. Let's say we put in the range of R3, okay? And then we still connect the edges. So you can see that these two no longer, okay, this one no longer intersect anybody. Okay, but you can't avoid intersecting this line here. Similarly, if you put this dot to R2, you will have the same problem. Okay, so that's mean there is no representation of N3, and it is not planar. Okay, so if you want to show something is not planar, you need to try all the possibilities and then see that it cannot avoid the edge crossing. Okay, if you want to show something is planar, you just need to find one planar representation. That's enough. Yeah. Okay. 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 Next. Next is Euler formula. And this one is a bit closer to what I do in my study. So let G be a connected planar symbol graph with E edges and V vertex. So E and V are numbers of edges and vertex. And then let R be the number of regions. Okay, so just now we met a region. Those regions are bounded by the edges. In planar representation, G. So the formula is, okay, you can find the region using the edge, number of edge and vertex, which is R equal to E minus V plus 2. Okay, I want you to believe this formula first. Okay, so I show you example. I show you this strength of this formula. So let's take maybe a square. Okay, this square here. So how many region you got? You got inside one and the outside one. Okay, so R is equal to 2. E is equal to what? How many edges? 1, 2, 3, 4. V 1, 2, 3, 4. Okay, so 2 equals to 4 minus 4 plus 2. Okay, so follow the formula. So maybe let's do something crazy on this square. Okay, let us add a few vertex and edges. Okay, so how do you want to do it? How do you want to do it? Like this. Take one more. Like this. Any idea or not? If not, then we stop here. Okay, let's count. So R1, R2, 3, 4, 5, 6, 7. Okay. So we got a R equals to 7. How many edge? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 edge. How many vertex? 1, 2, 3, 4, 5. Okay. So 7 equals to 10 minus 4 minus 5 plus 2. Okay. True? Yeah. Okay. So this formula never wrong. So this 2 is a magic number here. Okay. So 2 is a magic number here. So actually there's a name for this magic number. And we call it, and maybe I use purple. So purple is something extra knowledge. So this is called the Euler characteristic. Characteristic of the pentagram. Okay, so we can attach this Euler characteristic to different things. We can attach it to surfaces, to polyhedra. Okay, so just now you see the cube, right? The cube, or the what's that? The cube, yeah, the cube dotted cahedron. So this Euler characteristic of cube dotted cahedron dot the cahedron. Hopefully I didn't spell it wrong. Is 2. Okay. So you can see the cube looks like what? Look like this. Okay. And then the dodecahedron, I don't know how to draw. Too big already. And then this one thing is Euler characteristic of a sphere is also 2. Okay. So if they have the same characteristic, we will say that they are equivalent. Yeah. So how are they equivalent? You can try smooth out the edge here. Okay. If you smooth out the edge here, the cube will just become a sphere. Okay. So they are they are equivalent in the ring of we call the topology. So if you smooth out the edge here, then you become a sphere. Yeah. Okay. Yeah. And then it turns out that the Euler characteristic of surfaces break into 3 cases, which is 0, greater than 0, and less than 0. So what do I mean by that? We call the 0, 1 coil flat, and then greater 1 is a spherical, because you can see from this example here, when it is 2, it looks like a ball. Okay, and then the less than 0, 1, we will call it a hyperbolic. And these 3 surfaces, right, coexist in the universe. Depend on the gravity. These 3 surfaces coexist in the universe. So although you are living on a sphere, right, you think it is flat now, is it? Do you think it's flat now? You think you're walking on a plane, but actually you are just walking on the more locally part here. So we call it a locally flat. Okay. This one is extra, but we will try and prove this or use this Euler formula next week. Okay, we'll stop at the Euler formula. Any question or not? If no question, we will stop here and then rest until 11. In the meantime, you can come one by one and then collect your exam paper, and then you can take photos and then return to me after the reviewing. And you can argue marks with me if I miss some marking, because yeah, okay. Okay, so we will resume at 11, but in the meantime, one by one, you can collect your quiz pattern. Yeah, 快这里，快这里，快这里，快这里。我看住这个。
哦，
啊，呀，
I think 你是如果 direct 嘛，就是 direct theory 好像也可以的。第一啦，还有就是
哦，第二，
他这边有个啊，
啊对，他不是说有了，他是说有了这个就有这个，但是有这个不一定有这个。
哦，就是他不一定
啊，那个是convert 来的，那个是convert 来的。呀，convert 不一定对。
下面跟 circuit 不一定有那个，可是这个
对。
OK，
我懂。
对啊，
lock chain 一点。
这下是
会。Last 3 digit.
Sorry?
Last 3 digit. Last 3 digit. Last 3 digit. Last 3 digits. Last 3 digits.
不敢看，不敢练。而且当越讲问答，好，反正这是一个啊，这个核心痛都会痛，是哪里痛？在这里。哦，那完了，这还好，所以老知道了，但是可能重新也不同，就走老我见你这种导演那种，我被调动一下，一点你，我反高点，来就是我也啊，要重新我也是，那也撕掉这个了吗？没有，我觉得撕掉比较好，比较正。现在不懂再回一点。有些学好吃，有纪念，有些该都很高。哦，因为这刚刚一直是这个样子。等下我帮你淘汰一个。啊，我喜欢吧。嗯。Last week, 270. 你看让你知道在20分哦。哇，没错。因为条在长，我的全部短短的，爱出去。所以是短短的。自己这样走。你说你是817，他算是考，我知道。那我的，不要变你。5，那课我的用他的套路去。那多行累。 就这个不了，很多可能去死累这样，这些是什么？啊，你什么上？啊，算下来上哦。啊，你好像有做，但是好前他跟我讲可以 by inspection。啊，然后需要 by inspection。嗯。
5分多的也
希望要其实出来说讲40包用啊，
不要乱了，你看一下我乱有没有改。Last week.
感觉3种就行了。做问题了呢。上下都差不多，没有了。
来啊！哎，好像忘记你们2个都带来啊，忘记带。我查一下。
我有
有啊？去哪？You run got the exam paper yet? What the exam papers, right? Hả? Được không? Pasti gitu. Let's discuss. Please don't write note inside your exam paper, okay? Because they need to like submit back to the exam board again. You can write somewhere else if you want to take notes. I think I will put up this document later. Okay, first question is a yes or no question. You got 2 marks, 3 marks here. If you just put yes or no, you only got 1 mark. Okay, so you need to explain. So every step will earn you a mark. Okay. So not just a yes or no will earn you a 3 or 2. So you need to work. So you see, there's a warning here. No step, no mark. Okay. Okay, first one. The first sentence here is a command, right? You should move on to the next question. So it's a command, so it's not a proposition. So the question said that it's not a proposition, so it's true. Okay. A lot of you said that if then it's a proposition. Okay. You cannot just look at if then. You need to see whether the proposition, the compound proposition, the proposition itself is a proposition or not. Huh? What do you mean? That one is just but this thing is not a yes or no thing, right? Yeah, I mean, it's not a true or false. No, I mean, should and should not is not a true or false thing. You get what I mean? It's just you go and do, you cannot do. Whether you do it is true, is a correct thing, is a true or false thing, you know? Get what I mean? You get what I mean? So for example, you go and drink water, is a true or false? I mean, is it? If you drink water, is it true or not? How to say? But it's a command or it's an action. It's a not true or false here. You cannot verify it's a true or false, right? Okay. Of course, you can say should or should not. That one is like negation. I mean, not exactly negation, but it's opposite. Yes or no. I mean, should or should not. It's not the real negation. Okay. Yeah. So an action you cannot say is a true or false. Command. I mean command. Okay. Okay. Two. This one. Order is important. Order of a quantifier is important. If you swap it, it will give a different truth value. So I just put some simple example here. Some of you remember the hard. Let me finish this line first. Some of you remember the hard example in your textbook. I think quite good. Yeah. Some of you write it down. So quite well done. Sorry. Later you can come and talk to me. Okay. Maybe I mislook or what. I can have a look. But don't write on your exam paper. You can write somewhere else. Okay. For three, three is false. I think this one we already keep repeating this empty set question here. So empty set, there's no element here. If you take unions, there's nothing you add into the set. You don't just straight away add the set into the union of set. Okay. For the floor function is injective. Floor doesn't injective because different number can send to the same number. Okay, it's not injective. Five actually we discussed this in the class. We discussed the contrapositive of the statement. If A divide B, C, then A divide B or A divide C. This is wrong. We already did this in the class. But now I use the contrapositive way to ask you. Okay. So simple example is 6 doesn't divide 3, 6 doesn't divide 2, but 6 divides 6. Okay, so it's 4. Any question on any problem from question 1? If not, then we proceed to question 2 again. Okay, no question. Understand the solution. Okay, let's move on to question 2. Okay, question 2 is just asking you to build the truth table. I think most of you done it quite well. 10 marks. And then B, there's few ways to prove it. Either you use the algebra way, either you use the truth table way, either you use you can also use contrapositive, logically equivalent. Yeah. This is what I wrote for my answer, but you also can use a different way to do it. C I restrict. So C, you see, C and A actually the same, but C I restricted your proof using part B. Okay, so you need to proceed using the algebra way. Okay, so I ask you to use the table. I mean the identity table, okay, the formula table. Actually, these two are the same thing, right? If you notice, any one of you notice, these two is the same thing. Prove the same thing with different method. Okay. So this is the step. Okay, so you already see this truth table. I think everyone did quite well. Unless you don't study, then I cannot help you. P, I use this. So there are about 4 steps here, so I give you 5 marks. So you need to state all the law you use or the equivalence you use. So you see this as the S, see this as a T, okay, and then make this into a not S, not T imply, not S. Okay, so this one, make it into this form here. And here. So here is the S. Here's the T. The not T. Okay, so you can use B. Anything you want to re-see, you will see again in question 2. 2A that did quite well, 2A. Just some of you don't list enough the true value the possibility. Because 2 to the power 3 is 8. So there are 8 combinations you need to check for 2A. So there are 8 combinations you need to check. Some of you just check 4. So not enough. Okay. Anything you want to see again in question 2? No? No, then we try move on to question 3. Okay, question 3. So why I put question 3 here? Why they are in the same group? Because they can be proven using the same method, which is the inductive proof. Okay. So for inductive proof, you need to check your base case, assume inductive hypothesis and inductive step. So for question 3.1 here, what you can do is you write out what is this. Okay, write it out, and then see how you can make the left and right the same. Okay, you should work forward and then work backward and then see how they are equal. And then for 3.2 is a bit tricky here, so you need to know how to use this inductive hypothesis. Okay, so basically in the inductive step, you can break your subset into 2 kinds. One contain the extra element, one didn't contain it. Okay, so how to construct the subset that doesn't contain the extra element? That one is just inductive hypothesis. To count the subset that contain the extra element, you just add the extra element into the previous all the subset, and then you get all the subset in this way. Okay, so it's like 2 to the power n plus 2 to the power n. That's why you got 2 to the power n plus 1. Okay, but clever enough, some of you can prove these two without using inductive proof as well. Okay, so the first one, what you did is just compute the general n. Okay, and then you just plug this in, and then see that it's true for all n. Okay, general n, you can work it out. And then for this one, what you do is, because it's finite, you can ask whether an element is inside the subset or not. So whether yes or no. So there's 2 possibilities for a subset for an element to be present in the subset or not. And then you can use counting. That means 2 to the power n elements. Okay. So whether the element is 0 or 1. Okay, there's 2 possibilities whether they are in the subset. If you learn counting, then this method will become obvious. I mean, obvious a little bit. 0, 1. So in sub, not in subset. And then in subset. And so there are two possibilities here. Okay, any question on the question 3? This one is on the inductive proof. Okay. So question 4 here. So ask you whether it's valid using logic. No need to use the truth table here. So 4A here. Actually, I put some hints here. Okay. Because some of you look too detailed. Okay, what do I mean by that? Too detailed. So you break this into two parts. Okay, become Q or R, something like that. But they are not proposition, right? So in general, you just need to look at this as a whole. Okay, this is your P, or this is your Q. I call it C in this case. And then this one is not C. Right? You can see that the repeat thing. Okay. And then this one is not X. Okay. So a proposition and this one is inverse, right? Is this inverse, converse? Which one? Inverse or converse? I think inverse. Inverse. Yeah, this one is inverse. So inverse and the inverse of the proposition has no connection. Remember we taught in the class. Only contrapositive and the proposition itself. And then surprisingly, for 2, a lot of you can do it. So some doesn't imply all. So you cannot deduce for any games. Okay. I think this question also similar to Caleb and Jia Wei Wang. Okay. So you can listen a little bit. Answer is similar, around the same. The answer is around the same. I just changed a little bit the question. Okay. So far, okay for question 4. Question 4, okay. Okay. Keep going. So question 5 here. Okay, maybe this one looks a bit complex. Okay. But you can break it down. So what's given? I think we talked about this in the class. Given for all, for every, for all, for every, each, for each. And then there exists. Okay, there exists. And then if, then. Okay. And then the middle part, what are these? I already give you the notation actually. Okay, less than this number, less than a number, this number, less than a number. Okay, you don't need to know what I'm talking about inside there. You just need to use my notation. Okay, greater, okay, greater than 0. So what's greater than 0? Epsilon greater than 0. Okay, delta greater than 0. And then if this, then this. Okay. So first part is just to test the this thing for all, every, and then notation. B is provide the negation. So if you can translate this into mathematical symbol, that's easier to see how to translate, how to take the negation. So this negation is the De Morgan's law for the quantifier. So if you negate for every, you become there's this. Negate there's this become for every. And then negate P implies Q, you get P and not Q. Okay. So some of you negate this thing. R is less than 0. R is less than 0. So which is wrong? And then you forget when you negate P implies Q, you get P and not Q. Okay. Some of you write P implies not Q, or not P implies not Q. Something like that. Okay. So this is to check to test whether you know how to negate compound proposition or not. You can negate using De Morgan's law of a quantifier. Okay, so each of them will worth 1 mark, and then altogether it will worth 4 marks. Question on question 5? No? Okay. Okay, 6A. 6A, some of you did some, I think, silly mistake. I don't know how you do it. But intersection should be clear, right? Just whether both of them are inside the set or not. Cardinality of A union B, some of you make it into a multi-set. Okay, so you count extra stuff. Okay, so 2, 3, 7 already exist. So you don't need to count them anymore. So don't count extra stuff. This is not multi-set. This is just set. And work out the power set. Always you forget the empty set. Okay. Remember the first thing we proved is empty set and the whole set exists. Right? It's a subset of the set. And then some of you don't put a set bracket around this singleton. Okay. I don't know if it's forget or you don't know. Okay. So because power set, the elements is a set. So for all of them, you need to put the set bracket. Okay. And then for question 4, although I didn't teach you how to count the cardinality of Cartesian product, but you should know from the Cartesian product definition. Because what is Cartesian product? All the elements from the first one, you multiply with the second one. So when you do this, it's just multiplying the number of first set and the number of second set. So if you do it wrong in 3, okay, if you do it wrong in 3, but you tell me that it's a multiplication, then I will give you marks as well. Because you just compute wrong here. So I'll give you mark. Even though you do question 3 wrong, I'll give you mark on question 4. If you show me you are multiplying this number and the cardinality of A. Okay. Okay. Keep going. Question 7. Okay, question 7 here. So question 7 here, prove that any strictly increasing function is 1-to-1. Okay, this one I think I exposed this question in the lecture already, but we didn't discuss it and nobody asked about it. Okay, so I actually put this question very long time inside my lecture now. Yeah. So how to show this? Instead of showing if fx equal to fy, then s equal to y, we show the contrapositive. Suppose x is not y, and then we show that fx is not equal to y. So one technicality here, I will be lenient in your marking. If x is not equal to y, we can assume that x less than y or y less than x is the same. Just do one is symmetry. So if x less than y, since f is strictly increasing, fx is less than fy, which means fx not equal to fy. So it is injective. Question 2, show that it's injective. I give the hint here because I want you to use part 1. Okay. If you got this hint, you can see that this f is actually strictly increasing. So by part 1 is 1-to-1. How about surjective? Surjective here is not surjective because you can find a point here which doesn't have a pre-image. Okay. Any question on these two? Keep going. Okay. If you need, we will come back again later. So question 8. Okay, this one I think very close to the tutorial or lecture examples. Use Euclidean algorithm to find the GCD of the two numbers. I think most of you got this question right. Most of you get it right. Just some of you are very careless. Forget the minus sign, something like that. Yeah, most of you score this question well. Find the GCD and then use the reverse extended Euclidean algorithm. Okay, this one can skip. This one most of you done it. Correct. If you fail this question, right, you most probably fail the other question. So if you fail this question, you should be careful. I think you will fail the final. Okay, because I think you are not taking the class seriously, not studying properly. Because this is the simplest question in this test. Okay. Okay. 9A, 9 question 9, using the Fermat-Little's theorem. These two, I can't say. Okay. Exact question 2 is quite similar to the tutorial question. And there's one thing to note here for question 2 is you always use a p to the minus 1 mod congruent to 1 mod p. Okay. You can only use this when you know that a and m is relatively prime. If not, you cannot use. You can only use AP congruent to A mod P. Okay. So this is a lot of people fall into the trap. You didn't check whether A and M is co-prime or not. You just use it. Okay. So instead, I think in your class got 1 or 2 realize this. So they use the second version of Fermat-Little theorem. There's 1 or 2 in your class realize this. Okay. So any part I need to repeat for question 9? Or I move on first? Any question? Okay. Understand. Understand. Need to repeat? Hey, where's my attendance list? Done? Hold on. Okay. This call, huh? This call. Okay, this one. Okay. 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 Okay, next one is the Chinese remainder theorem. This one is the classic question. Classical question. So most of you did mistake when you find the inverse here. Okay. You don't find the inverse here, you just straight away evaluate this and then put this number in. Okay. This is not this 20 mod 3, not the capital M mod the small m. This is the inverse of this. Okay. I wonder if you like do the tutorial question or not. If you do, I think you will realize that there should be an inverse. It's not just mod. Okay. So it's important to do the tutorial question to test whether you understand the theory or not. Okay. And then some of you just keep using the Chinese remainder theorem. You just go and test the number 200 and 250. Test the number whether they divide by 3, 4, 5 or not. Yeah. So I'll give you mark also if you do that. So you count it and then you show the step. But some of you, I don't know how, you just put a number there, 226. I also don't know how you get it. Maybe some angel tell you it's 226, is it? There's no step 1, so I don't give you mark. Yeah. Okay. If you wrote the step inside your draft, you should give the draft to me as well. Or you just put it inside your exam paper. Okay. Don't write working on your draft and then you give final answer here. I can't give 7 mark to just a 226, you know. There's no step. I need to give step by step marks. Okay. So the scaling for this exam will be, you have your final score, and then we'll multiply 0.3 as 0.7, and then plus 30. Okay, that's mean the free 30 marks for you. Everyone will stack up by 30. I don't want to fail you in this midterm, but if the midterm I gave you, you are less than 30, you are in dangerous zone. Okay, you probably fail the course. So you make sure you work hard in your quizzes and your finals. Otherwise, you will probably fail this course. Huh? Okay. So in this scaling, right? So for those that are more than 80, I think 79 also, you will get pushed to 85 and above. So it's 4.0, which is, I think, is ideal for me, because above 80, I think it's quite good. Yeah. And then the rest will be scaled accordingly. I think at least one grade up. Yeah. You can check for yourself, but at least one grade up. But 81 will push to 4.0. Okay. I think your class is still okay because the lowest one is 22. Some other class got 10 something. If 10, this means I don't know what you're doing in the course. Not studying. There are some, for example, the truth table, the 10 marks should be easy to earn. Also, the Euclidean algorithm. Also, this one, so 7, 10, 17, 27. At least 30 marks here you must earn. Then other, so to get 4.0, you need to really done good in my exam. But the rest should be fine. Should be okay, normal. Okay, any question you want to revisit? No? If no, you can, yeah, for Jiawei and Caleb, how? I think it's in my room. When you guys want to see it? No, they are replacement exam. Next Tuesday. Next Tuesday, my office hour. My office hour. After your class. Okay. I'll bring your exam. Because that day I also need to bring 40 MT. So I think your exam paper still with me. I'm not sure why not bring it today. Let me go back and check. Okay, the rest you can what? Okay, so take pictures, don't draw on your exam paper because later need to submit to exam board again. So you need to give me back. If you don't give me back, I cannot change your mark, okay? If I need to change your add mark to you, I cannot add. I need your physical exam paper. Okay, if not, you can start doing the, if anyone want to have some argue, I mean, you want to talk about your marks, you can come here. And the rest, you can start doing the tutorial question. One by one, next.
Optional definition 是它可以变为 true or false。
对。
不对。
那个是对，但是你没有解释为什么它是 false 呢？不是吗？
这个。它是往后
这总分多少？OK，我知道flow在哪里。我可以给你3分这个。因为你不可以 suppose y 大于 x， 你要 suppose y 不等于 x， 然后你才用 y 大于 x， 就扣你1分。 哎，还有吗？气还有吗？气还有吗
没有去了。
？OK，那我看一下。啊，嗯，
就跟你差不多一样，我是才开的默契，才从默契的默契，
你猜怎么这个梦？
默契才开。
哦哦，所以你是用对？没有啊，你这个用4啊，你就这个对吗？
对，我是5嘛，然后我把那个次方拆开，
要拆成5，不是拆成4哦。你这是拆成7，
不是它是
那个
m 减1，它的次方
对，没有，因为这个刚才我不是讲了没 ？n 跟这个5，我不知道它是不是 copine 哦，对吗？我这个不知道是这个要1我才可以用，
没有，如果不是1呢？
不是1就不可以用这个，是不是啊？
应该是什么这个？
这边没有讲 GCD of n 跟那个，
所以我要算出来还是1。
没有算不出啊，我没有给你，我都没有跟你讲什么是 n，我没有跟你，我没有告诉你 GCD of 这个 n 跟这个35或者呀，因为我没有告诉你它的 GCD，
冷气也是可以，
这个气可以，这气可以，这气可以，
这个 n
什么？
也不一定
这个
没有 n 7 is n mod 7吗？对不对？这个跟 GCD 这个不需要有 GCD 的 condition。
啊？对，这是公式来的，分吧？
对呀、回去看一下那个公式。
另外一个分
对呀、另外一个分嘛，说这两个是equivalent 算 equivalent。哎，这边的时候要 GCD n 跟7等于，哎，对吗
所以是总的数就不用理解这种。
？Yes，这个是4分是吧？我可以给你1分，你对一半。没有看这一半，在哪里啊？
没有，没了。
怎么会给到啊？
在下面，
这个没了。然后给几分？
1分吧，
一
半，对一半，对一半给1分，
一般，那里是一般。
就是这个一半和这个一半。
1分。
加1，没有啊，
没有，
这是第7，我7跟
跟5.0啊。
我考卷我6点。
啊，有没有？哎，可以帮我 OK，等一下，等一下帮我排一下那个跟顺序
你想
排一下
问这个？
OK 啊，要问，
你想问这个？
要问，
对，
问吗？要问吗？
它一样。
但是你做法跟他不一样
嗯，
啊，不一样。本来是0分的哦，等1分嘛。呀
能问这个？
，OK，这个怎么？跟你在做什么？What are you doing？
然后就拆了以后，这个就是你把这个看成一个整体的 VP 或 P 也是可以的。
可以是可以，但是你没有用 Part B，你用 Part B 吗？
是真棒，
你不叫你用 Part B，
算
嗯，
真棒吧。我真的没有。
你不叫你用 Part B，我可以加多你1分啊。因为如果你用 Part B 的话，如果错啊，我会给一半高过一半。但是你没有用 Part B 来 prove 的话，我就给2分吗？可以吗？合理吗？对呀，还有吗
让我有点笨了。
？OK，你看一下。
记要
哎，这是第几对啊？确实
真的。
是，哎呀，我一直弄错年龄。你是赵静不是？哦，在这里。OK，可以。对，我在。OK，来，这题
这题我觉得对，可能
你觉得你是对的，
这个
写错对吧？刚才你在干嘛？
然后我也用了 Copy，
你用了放屁。
把这个部分简化了，然后这部分简化了，最后就是他们俩一样的，一样的。
来，我看看你的问题。来，坐坐。那你在干嘛？
引体声。
你这个是 not 这个，and then 为什么 prove 这个是 tautology，然后你是 prove 这个东西？
它不是我们
你
要
prove 它的 contrapositive，
对 contrapositive，
但是我要你真的不是这个东西哦，我要叫你真的是这整个东西是一个 tautology 哦，我不是叫你真，我不是叫你真这个 imply 这个，你知道我什么意思吗？
我知道，但是
哎这样
它的形式我还是真的他们俩是一样。
OK，我知道了。这样你是说跟刚才那个人差不多一样，跟赵静，对吧？但是你的论述有问题，哪里？就是你真的是这个东西，我要你真的是这个 is OK，可以吗？这两句话不一样，你真的是这个，我要是这个，可以吗？可以吗？但是你做的这个东西可以证到这个东西
是可以。
啊，是可以，但是你需要知道这两者是不一样的东西，
OK，
对吧？
那我这两步是已经证了，就是它是做到了。
但是你没有写，
总结算吧，
我再加多你一分，就一分吧，不可以两加。但是你要知道这两个是不一样的东西
我想知道这两个区别。
啊，这两个区别是什么？这两个区别是什么
哦，对，我不知道。
？OK，我慢点再跟你讲。
好，
先解决掉这三个，
慢慢
慢慢讲。啊，就这个哈
还
，OK，
记下一个。
第9个，
很多。
对，为什么成绩了？为什么最后改成1分了？
因为我跟你说要用那个另外一个分码里的表可以用那个 AP 减1等于你是不是用 AP 减1等于？
费马小定理。
对，对，你用 AP 减1来，对，不可以用那个，不可以用那个，因为那个没有 ACD，我没有跟着注你他们的语呀，不可以用那个。哎，对，
那没好，
OK 啊，OK，Thank you。
就那点，
呀，帮我排一下那个数字，就是跟着顺序。
然后这个是
呀，对，
就是专业的，
把不同专业的丢在最后的丢在前面。呀，
可以问到
那谁？呀，
very quick
呀，
那个反光不透啊，因为我看起来好像有一点晕。
OK，其实这个我有给人家多1分，因为你这个你只是讲有可能，但是你没有告诉我是什么，就你没有给我那个 example，你只告诉我有可能会发生吗？懂我讲什么意思吗？懂我讲？
其实我也不太确定那个题目讲什么，只是觉得这个大概好像有一点对，这样我就拿来问。
哦，for example 这一个哈，这个 example 好像是错了。这个如果你转来转去，它是一样的东西，但是有一个句子是 such that 它是错的，但是你这个讲的道理是对的。哎，可是不是这个不是道理，这个只是 translate 我的那个题目吧。OK， 没有，就1分吧。OK，你这个例子是错了，因为你这个反来反去是一样的东西。
对啊，我都忘记到底在做什么。
哦，这么
你是说这个 derivative 啊？
对啊，好
我们
到底问的。
这个我不知道你讲吗？ OK，你要用那个 gradient 的东西是不是？但是我们的课没有教过，
对，但是题目上也没有限制。
我题目上是没有限制，但是不建议。
不建议。结果倒是。
给你们分。我只会给你加多一分吧，我好像给另外一个班也是加多一分。
这样。
因为这个部分有3分。如果你不会用我们课里面的东西的话，代表你不知道我们在干嘛。
我不知道，之前我quiz的时候用derivative 给分了，所以
怎么可能？
我找一找你让
你去找去。
要给，那确实
应该是没有给满的。
好像
我应该是没有给满，不可能给满的。
但
是这个我真的不知道你在说什么。
上面这个就是
我知道你要讲什么，但是你怎样 relate 去？
它是一个单灯的一个，对，它是一个 one to one。
不知道，我真的不知道你这边要讲什么。你把很多个对的句子放在一起，但是他们就
没有
不知道怎么连接。
但是我觉得我有写了
你解释。
我解释说，它题上是要证这是一个 one to one。
对，没有错。
那我就说，对于每一个 x 对应 y，它 x 增加的时候，y 就是 y 也是增加的，然后找不到两个相等的，找不到x 就两个不同的，就两个怎么说？我说
那你想想，你再告诉我。
就是在定义域上面找不到一个 x1和 x2不相等，但是 x1等于 x2的情况，就在整个定义域上找不到自变量
为什么呢？
因为这是个单流理动的，就是
不能够，你一定要告诉我为什么它不等于过后，它就
因为它只有一个值和它的对应，这是个很好的，就是一个。
就是你怎么从 strictly increasing 结论得出它是完？
因为这我说了找不到一个。
你怎么会找不到？你要告诉我怎么找不到？
因为它是一个单调理动。
什么叫单调？对呀。
因为它是一个 straight increase。
怎样找不到？
因为
什么是 strictly increasing？
就是当 x 增的时候 y 也是增
所以
它是一个单调
对，
所以它不会出现说两。
所以就是我答案啊，所以就是我答案啊，你有写出这种东西出来吗？对啊，这就是我答案啊。你没有这样写，你直接从这步跳这步。
Suppose x without generation。
我没有给你放啊。给你。我可以给你2分。我可以给你2分，因为你是没有写1，你没有写好来2，你没有真的引用这个，你直接说，可以吗？
可以了。
可以啊。这里有1、2、3、4加上，对不对？
对。
还有吗？
没有。
这个是9比30的。第7题，34的第7题。
放那里。
Hello. Before you go, please return your exam paper and then arrange according to the student ID. Thank you. 你在干嘛呢？
在这里。
对呀，你做了什么事呢？
就是在这一处，
对。
那个 passport。
B 的 B 哪里是这个哦？B 是这个是 tautology 哦，关这句话什么？就是这一个 is a tautology 和这一句话有什么关系？你为什么可以有了这个你就用这个？ 看得懂吗？
在证明。
我知道，就是怎么从这里去到这里，这是你用的吗？对不对？你这一步证了这个去这里是核心，但是你忽然间你用了，他们是 logically 啊？为什么可以这样？
因为这里
嗯，
用正在这里。
我知道，但是这两句话是不同的东西啊，对吗？
也是从 must be 得到的。
怎么得的？我不知道怎么得哦，你要告诉我怎么得哦，不能这样得的哦，得不到的，得不到的。这两句话是分别的东西，而且他们好像是没有联系的。嗯，你看这个符号跟这个符号是不一样的。OK， 然后这个是这一整句呀，不一样的东西 ，get 不到，不能 get，可以吗？想一个，不能从这里去到这里。嗯，
我想表示不是这个意思。
但是你用的就是这个东西啊，对吧？OK， 如果你要这样的话啊，这个其实在班上有说到，不是从 B 进来啊，这个是 contrapositive 来的。假设啦，我们从班上开始，班上有说这两个是一样的，然后你就正到这里，
是要走那边线。
and then， 所以你是说这一个变成这一个啊，对不对？然后你要解释为什么这个是 tautology 就变成一个 P implies P 的东西哦，对不对？所以这个不再用 part B 的东西啊，是也不是，对，很乱，而且你这边也没有用 law， 也没有告诉我怎么 law， 这题5分是不是？我可以加1分吧，
好不啦？好，好没。
因为你也没有告诉我为什么这是 tautology， 用什么原因，你没有告诉我什么原因，然后这个原因是因为 P implies P， 也不是我这个 B 的东西，这个是 contrapositive， 这个也不是 part B 的东西，然后中间你用的你没有告诉我是什么，
这还要写出来。
要不然我为什么给你们那个表格啊？
更好理解。
因为我在班上一直有想到这样子，对吧？还有吗？没有了。
这个是
30。
我
OK， 对，谢谢。
然后我让他这个 x 平方的问题，但是当等不出来时，就是说换 x 现在不相等。
你这个在干嘛啊？我是 floor function 哦，为什么 fx 突然变 x 回去？
我要找一个反例嘛，要证明。
可是我已经 fix 了，我的 function 是 floor function 哦，就是我的 x 是长成这样的。那么你忽然讲，你要反例，你要找2个点给我，不同点，但是送去同一个地方。OK。
找一个方式，然后证明
不是找一个，要任意一个 strictly increasing 的 function， 我说它是 one to one， 不是找一个，所有的，不止这个，所有的都要。所以你们很多人也是给我一个呀 ，OK， 没有，对，
对，我是这样的，你们不懂。
先生说
发答案在木头上吗？
可能会之后了，之后 OK。
这个我知道证明了，就是他
呀，对，你说。
就是这个与一是1分吗？
OK， 没有错，这个1分，
这个1分，
这个1分，
这个证明它是整除的是0是
2分 ，OK， 1分1分，对。
这个没有1分，证明是
对，这是1分，然后你算了这个是1分，有3个东西要算吗？
我算了这
第2个你算了，18n 你在哪里？看不到18n。
这个
啊，但是你算错罢了，是不是这样说？
没有，我这个给到这一步，这个是我最终的那个，我这个知道这一步也是。
我知道，但是你加起来的时候算错，是不是？里面都是0，不是2。OK， 对，3分。哎呀，没有，这题就是
什么？这个是3，
这个是它的 inverse， 这个不是直接取 mod， 这个 m1/8 是一个这个乘这个等于1 mod 5的东西，这个才是 m1/8，不是
所以我应该是就是这个是
这个是2吗？13，哎，对，这个是2，对，什么东西乘2等于1，对，对，
这两个是对的，但是我这两个不是，
但是你的算法是错，
就是不是我可以这么写吗？
不可以，我已经给你看了，这个2跟这个3都不一样，你可以懂，你得到的方式是错的，你只是刚好算到那个数字，可以明白的。
所以我应该是这个算完之后也是2，
Yes，
我应该是有这一步得出来得到2之后，我再用3乘
Yes，这可以 ，OK， 加1，哎，加几啊？加几了？哎，这个是什么来着？所以我现在给你几分？刚才刚才2分，现在加1分，3分，19是什么？OK， 是5题的第9题。OK， 好。Yep.
For this one, I said that they don't have the same time.
Where's your true or false? Why you didn't write true or false?
I didn't write true or false directly. I just explained why I chose it without saying it directly.
You should say directly first and explain. Okay, let me see. Yeah. So like why you put here, I also don't know. Okay, ignore that. So next time make sure you write clearly, okay? Yeah, I think this one can be. This is 3 marks, right? Or is 6? Just this one for for question 1, I mean.
Oh yeah, for question.
Okay.
To see, in my own way, I showed it was a pathology, and then you didn't just more. No,
Let me see. So why are they the same?
I didn't. I showed it.
No, I mean, why are they the same? You say because they are the same, so it is a pathology. So why are they the same? Have you shown they are the same?
Over here. Whether it's negated or not, it's keep going.
Wait. So what's this 3 step here? I don't know what's doing here. There's nothing.
No, the thing is, I understood this.
What? Only you understood. You need to tell people that you understood, right? If not, how people know you understood or not?
No, because this showed how I got.
Yeah. I mean, okay. Now I give you a chance to explain. So you explain yourself. So what are you doing in this 3 step? You don't, I mean, I show you the question. I can show you the question. I show you the question. Yeah. So why you put
Okay,
this
so
two? Yeah.
if P is in Q, then R, right? So
Okay.
if R or P or negated Q, okay,
Yeah. So what's the relation between these two?
they're both the same.
So why are they the same?
Obvious.
Because
What? No, cannot. You should tell me.
what I explained it, like, you know,
I know, but you don't write it down.
please.
No. I mean, no. I can give you some marks, but you need to explain to me now. Now I give you all the chance. You can go and check your definition of what, and then you explain to me now. Yeah,
I don't even remember the question.
I give you see the question. I let you see the question.
Yeah.
What? What? I mean, these are not the same. This got two arrow. This one no arrow. This one got all, got n, got the wedge, got the cup, got the cap, got the negate. Different
How?
symbols. Why are they the same? Right? What? I asked you to show. Of course, it's correct.
So if I go show right now, you'll do
Yes,
it.
yes.
Yes.
Really? Okay,
Yeah.
I'll do it right now.
No, I won't give you full, but I will give you some.
Even some is fine.
Yeah, sure. Yeah, go ahead.
Okay, wait,
Yeah.
I have another one.
But you don't draw on this paper, okay? Okay.
如果过后再问你可以吗？先拍起来。
如果能够现在就现在哦。
现在天荒地老哦，
天荒地老
他就吃了。
Okay.
Like I did the negate. It's what you wrote.
孩子吧，
去吃哦，我今天给他吃了不用。我昨天就跟你讲了，
Okay.
答案都对的哦。
Okay, the exist is correct. Given. Okay, because it's for all. But what's wrong is this one is wrong. Less than is wrong. Less than is wrong. And then if it's wrong, then it's wrong.
Okay.
And then this one is wrong, but this one is correct. So that's why I give you two.
Okay.
Okay.
Or this one.
Mm.
I showed it was injected. I got this wrong, projected, but
Yeah,
this
okay.
one is right. I showed that it was.
How you show?
I don't remember. I showed.
No, you didn't show it. This one didn't show it. This one didn't show it. So I put this one. That didn't show it. I know. I know what you wrote, but this one didn't show it. Didn't did the proof. Didn't prove it. You just check few points. It's not enough. You need to check all points.
That's how I checked.
No, not enough. Because there are infinitely many points. So you need to produce infinitely if you want.
For this one, it's still wrong. I just showed with using the graph. You said it's
Definitely wrong, but I give you 1 mark because somehow you get the idea.
Okay, I'm gonna go show you.
Yeah, you try.
这个是手机。
1 2 3 4 5 6，好吧，你们去吃啊，不然等下太迟了啊。
还是可以上去哦，
什么？
这个可以播上去哦。
应该会。OK，你们去吃啊，拜拜。OK，去吃，拜拜。1 2 3 4 5 6 7 8 you got 8 of them. You only right?
Hey, really? Can I see the question?
Yeah, you can see on the.
这个是可以是的。
不 valid.
如果我可以做到 conclusion 的话，就是代表它是 valid。
是，但是问题就是你的中间是错了，你明白吗？就是我知道你可以做到 conclusion 是 valid，但是问题是你中间的步骤错。你是谁啊？1 2 3 OK。你中间是错的，你中间为什么错呢？给我看一下。对，你怎么可以反着推呢？这个箭头是往前的哦。
Control positive。
Control positive 是 C to not X 哦，不是 not C 哦，所以你推不出什么东西从 not C 的，你懂吗？没有 ，I mean 这个是往前嘛，这个箭头，对不对？但是你怎么可以从 not C 跑回 X？ 理解吗？理解吗？不理解。你看你这个箭头是从 X 有了 X，我就有 not C， 但是你有 not C，你怎么可以回到 X 呢？这箭头又不是从这里去这里，对吗 ？OK，呀，箭头错了。哇，你还背得出那个名，还很厉害耶。
什么都完。
我看到你们有些很神奇啊，连那些名字都背得起来。你这个为什么哈？那个是 any function，所以是要所有的 function，不是只有一种 function 吧？
any function。
呀，any 是所有的啊，所有展
不是 any example。
啊，不是，
可是题目不是给了那个 SQ，
这题目给了 S，什么是题目给了 S？
现在题目是给 SQ 的。
7A 没有啊，
没有啊，
没有 any strictly 所有，
其中一个
不是其中一个不够，所有
一分也没有啊。
any 嘛是 anyone 嘛，
一个一分。我忘记我没有给过人分了，
我的跟他一样，
我有给你分吗？
我的0分。
0分啊，这样就0分了，我好像全部没有给分。没有分哈。OK 呀，没有分，sorry 啊，全部人都是一样。
都没找到。
啊？没有看到没有答案啊？就是你要 prove 这一句话吗？但是 prove 这句话，你可以 prove 2 probability。
我理解成任何一个。
对啊，就是任何一个，只是你的任何一个跟我的任何不一样。它就是任何一个，你要 prove all，任何一个就是全部。哎，对啊，这类东西，对对对。哦，为什么这里就有5分哦？这么久5分呢？啊，为什么我只给你5分？这样神奇啊？可能我算错诶，我记错号码，给我看一下。OK，应该是满分，我觉得。T，怎么你忽然间漏一个 T 在这里？OK 啊，我觉得 OK。我觉得 OK。哦，你是忘记写这2个，对，很多人忘记这个 FFF 跟 TTF，他们只做到这边吧？
要下一个。
没有啊，他们好像还有很久。OK，应该是10分，我漏，应该是看错了。这题没有了，不是？这题还有吗？还有吗？
没有。
没有了，525，这个哈。OK，好，谢谢。谢谢。
老师这题为什么不可以？因为老师你是说，老师的题目是
呀，
老师哎，刚刚你因为老师题目是 yes part 有 show，
对，
因为 part 有理解它是这个 contrast
啊对，
所以我现在有的这个是我这个嘛，所以我就用这个 contrast positive 这个，就是我做的一个新的，就来满足它这个整个东西，就是来 show that again 这个是它的逻辑。我就是 by comparing by using the contrast positive 比之后，我们可以用回这个东西，就跟这个对比。
你怎么用？
就是类似我这个东西嘛，是来自这边的，就是我现在我这边做的一个是来自这边，对，因为我们有了判例嘛，就整个就是高特逻辑哦。
OK，你是不是在说？
因为我就是塞这个东西进来这边，我做这个，都因为我们有了这个判例嘛，所以我们就可以秀在它这个其实也是它的逻辑哦。
对的，我再看看你在，我想一下，我整理一下你在说。 我教你说的 P implies Q 是一个 tautology。OK， 你做的是这个东西。你用 not P implies not Q is tautology to show that Q implies P is a tautology。你就在做这件事情。你 prove that not 这个 imply not 这个 tautology，然后你要回答我的问题是 Q implies Q。
你就是回答回之前这个就是这个逻辑，
对，但是问题是你在做这件事情的时候跟 B 有什么？
因为我们知道 B 它已经是 contrapositive 嘛，我觉得只是用回这个就是好像 AB，所以 BC 就 AC 了，对吧？
你不懂？等，你懂我在讲话吗？先，
我懂，就是用回你是说我这个用回这个来 prove 回之前这个是这种逻辑嘛？因为就是类似现在我有这个 A，我有这个 B，所以我现在我这个对了啊，就 B 已经是 proof 了嘛，所以我就用 BC，AB，BC 之后我 A 等于 C 哦，就类似那个款。
不懂，我不知道你在讲。你懂我在讲吗？天啊！你懂我在讲吗？
你就是说我用回这个来 proof 回之前那个就是一样嘛？
不是，你现在要证这个是个 tautology， 但是你去证 not 这个 imply not 这个是个 tautology， 对吧？你自己写的，not 这个 imply not 这个tautology。
因为我拿回这边 concept，因为你说用 part B 嘛，part B 就是
对
part B 就是 concept。
对，你听你，
所以我这边收回就是对回前面的，
对回前面呢？
这边就照回前面就是拿回 part B 的，就是类似 transitive 啊，老师
哪里有 transitive？ 我看不到 transitive。
没有，就是因为我们第一题我们这边嘛是已经是 proof 了这个，
对，这整个东西，好，
这个就是来
你知道这个东西跟这个东西是一样的吗
是啊，
？OK， 好，
因为就是 transitive A B B C 之后 A 跟 C 是一样啊，
可是 A 跟 B 有什么一样？A 跟 B 没有一样啊。
就是 B 我们要让它有联系吧，就是 B 吧。
B 跟 A 有什么联系？没有联系啊。
都去啊，
没有联系，
没有联系啊。
有这个
强行
一个不是你看
是 tautology 是一个
你看
OK
全部都是 T，
我们不是说 P 是 tautology，Q 是 tautology，就是 P 等于 Q，你知道吗？P 是 tautology，Q 是 tautology，不代表 P 等于 Q，知道吗？
这个可是这个跟这个好像不一样啊，
什么？
这个我们已经有中间人了，就是那个 B 吧，你就是
只是用 B 去 prove 这个吧。
对呀。
换 A 是
啊，对。
可是我有这个
你有哪一个啊？你有那个，我知道你有那个，所以我才说嘛，你有这个吗？然后你要证明这个吗？对吗？这个是你在做的事情吗？你有这个，你要证明这个。
因为我们知道了这个是全部是 tautology 嘛，所以我们现在有了这个就就是 by refer to 这个 contrapositive， 我们就可以得到总共就是
为什么证明了 contrapositive 是个 tautology 就证明了这个是个 tautology？ 为什么？
因为
他 B 没有讲这件事情啊，他 B 为什么在讲这件事情？你解释给我听看，为什么这一句话是个 tautology 会代表这一个是一个 tautology？ 为什么？为什么用 part B 可以解释到这个东西？你讲给我听，为什么？我不知道可不可以，但是你讲可以，你试看。
老师重复一下，
重复一下，就是你证明这个 statement 是一个 tautology，OK， 你证了。你现在要用这一个 result 来证明本身这个 contrapositive 是一个 tautology。OK， 看吗？你看这两句的关系，一个是 P implies Q， 一个是 not Q implies not P 嘛，对不对？看一下这两句的关系，有看到吗？有看到啊？所以你真的是这个东西是一个 tautology， 怎样可以证到这个是一个 tautology？ 用 Part B， 你讲用 Part B， 怎样？怎样？
我应该明白老师说的漏洞了。
怎样？
因为它就是类似，有点难解释这个样子的话。
我也是觉得有点难。你如果想得出的话，
因为我之前就是因为它就是很 transitive 啊，我就是这样子。
没有 transitive， 没有，我帮你讲看。
因为它这个是在这边嘛，所以它这个是在这边，
然后
所以它这个就还是都是逻辑。因为我们两个东西都满足了这个嘛，所以这个它本身就是多逻辑。
那你也只是证明这整个是多逻辑，你有没有证明这个是多逻辑？这个你还是不知道它是不是多逻辑？就是说，你知道了这个是 tautology， 你知道了这整个是 tautology， 你怎样知道这一个 part 是 tautology？
因为它 transitive 它是一样啊。
哪里有 transitive？ 没有这种 transitive 这种东西，没有 transitive 这东西。OK， 你要的是这个东西，就是 if P imply Q is a tautology and Q is a tautology, then P is a tautology， 这是你要的东西。我感觉好像是没有这个东西啦，就是你要，你有这个 ，OK， 你也证了这个 ，OK， 但是你要推出它原本的那个是不东西，我觉得好像没有这个东西。
那没事，当然不是。
啊，
真没事。
没事。
因为我之前是想要 transitive 的东西，对，因为我们已经有了这个。
对啊，有了整个，有了 Q。
没事，老师说没有就没有了。
我没有讲没有，但是我觉得没有，你可以去想一下。我觉得没有啊，你可以去想一下。我觉得有错，有看到example，我觉得有看到example。我觉得有看到example。
可是老师，我们现在，
除非这句话是对的，这句话是对的，你就可以对；这句话不对，你就不可以对。
对，有那个。
这么你这样哈？
有看到example，我想要还有问题了。
OK，
因为如果我们好像 T 嘛，是虽然我们这个正两嘛是，可是这边 force 的话，它这边我们这边，等等，
因为你这边如果 force 一些东西，这边
我再整理一下，我换人的。
哎，可以第几题？哎，怎么我好像以前没有看过你在我班这样？安静啊 ，OK。
知道这是什么意思？
哦，你做一半吧？
什么意思？为什么？
所以这边有8个可能性，只是4个。
什么意思？
啊，
但是我这个 R 的话，这个意思是它的真值跟 R 是要确定，可是你选了 P 的。
哦，
对，然后对面讨论的话
我猜一下，
真和假的2个是吧？
哦，是吗？
对的。
哦，你分开做啊？
对，因为我之前跟
你从哪里发明的这个方法？
我只是突然觉得这种我可能会更简便。
更简便啊？
因为刚好它就可以用 R 表示它的真值。
我觉得应该你 R 是什么？你 R 是什么？
R 就是这个 R，就真值用 R 确定就是它。
这么这边会 TT
因为这是 B 是 T，因为他教这个 P 是 B。
哦，我知道你要什么了。OK，可以，OK 吗？好，可以，就这个哈。第二题
还
的，
有还有
你看我看见。对，你是这个。
还有，就是这道题。
Yeah，
这道题它这个 Cn 就是排列组合里面。
我知道，
对，然后 Cn 的表示意思就是它每个单独拿出来的。
我知道。
对，然后这样意思。
但是你没有证到这个东西啊，这个我不知道为什么对。
这个不是那个裁剪吗？那个
哪里？
题
没有，
就是我们考完第2节课就讲的排列组合，就是这个。
我知道，
这个就是社会现象。
我们哪里有？我们之前也是，我们那有证明过。
这是我们高中学的，我们高中就是这样子的。我们那边高中都这样子的。
我知道，但是
因为我之前高中有看过高数的书，也是这么证的。
我知道，但是我就是要你们证明这个东西。如果你要用这个，就是要证明这个东西。我就所以，如果你要用这个，你就证明这个东西哦。但是你没有证明的话，
太简单，我后面还写了点文字。
对，所以你没有证明呀，对。如果你要用这个，这样你就要证这个东西给我看。OK，
还有这个我用的是 Ctrl Division 就反证法，就我不是要证这个嘛，就我先说这个错的，因为本来就要证这个错的，所以我就先说这个对，然后最后是说了它是错的，比如说它不可能，因为它严格单调，它不可能有相等的性嘛，就是当 x 不同的是。
If it is not 1-to-1，
对，就反这个法。
你 suppose 它 not 1-to-1 嘛，对不对？
对。
So that's mean
对，然后这是不成立的，所以它是1-to-1。
对，你给我
可能自由解的。当时
你给我想想，我知道你要这么。
当时我只想这种方法就有点复杂。
But we know that is
因为我还加了个严格的。
啊，对 ，OK，我觉得你对。等一下先啊，这个地方有一些错是这个是OK，你 not 当补完了，你不可以直接跳去这个，你应该 suppose 它这样子先
之后是吗？
啊，因为你就 start with 它不等于，但是它等于嘛，对不对？但是你可以知道它们其中一个一定大过其中一个，因为它不等于。
那它不是已经单调了吗？所以说
我们要单
就先随便设一个，就 x 跟 s 的大小是可以不确定，他们两个随便设一个大于。
对，
随便设一个就跟这个差不多。
不，
就随便先设一个 x 一个 x 了。
我知道，但是我是说，你不单调就是不1-to-1的意思说，这个不相等，但是这个相等 ，OK，但是它没有
也是不相等的，它大于。
你不知道这个不相等到底谁大谁小。
所以说我这测试位置数就是不一定 x 必定也可能 x 大。
随便设，对，这个我可以给3分啊。
nice， 我也84。
OK， 好，
谢谢老师。
这个是在第7题，还有吗？
没有，其他都就。
我看一下你是523。立坤哈
Yes。
第7题是5分。
好的，谢谢老师。
OK， 好。这个谁啊？
我的，你知道。
先改出这个
第3题，就是为什么会打个问号？
你在干什么？
我感觉是对的呀。
你是在干什么？
就证这个。
我知道，但是你在干嘛？
就是两个相减会得到这个，就正它减它等于0，就能证到它等于这个嘛。
OK， 可以，好。
对，
然后
呢，确实是等于0，因为
你这个1/1这些全部通了，
因为它这个 n 就等于1/n 嘛，就是它这里不是有个减 n 吗？
对。
我把这减 n 放到这里
OK，
然后就
你说 n 减这个东西啊？
对，就变成1/1，然后这个就带过去2/2。对，然后就变成 n 减1。就等于。
OK， 所以你是其中一个没有用 inductive 部分。
对。
这题几分
？6分。
6分。
对。
对。 这个加7，还有吗？这题没有，
没了，
还有吗
没了。
？OK，526哈，李毅选
这个电话来的，这上面有。
OK，好，
我想问那个，
嗯，
现在上课的这个，
也
我想正它，
你想正它 ？OK， 好，OK，
就是我如果说 R 有意义的话，
什么叫 R 有意义？
就是一片区域，如果只有它一个，我认为是没有意义的。
什么叫一边区面有一个
就是
它这边
这一道
R1嘛，外面就R2咯。
对，但是可以这样，
你就
就是但是如果这么一大片地方只有一个 R1，我认为去定义它
有意义。比如说这个的话，这个就 R1咯，就外面整片是一片，这有意义
是这个意
啊。
思。
然后
但是呢，我就觉得，
你这样，
就是我是想从
你这样，
因为我们要去分它的那个角度，我是这样去
好
考虑的。
必须
所以如果分它的至少就有2个，
没有一个 R 也足够，一个 R 也足够
那。如果我从2个 R 开始讨论的话，
你还是要从一个 R，因为一个 R 也成立。
一个 R 也
一个 R
那我再去写，我
有一个也对，这个
应该差不多
你看，这个是你的 base case 来的，其实这是你的 base case。
我觉得应该
哎，一个点也可以，是不是？一个点也可以呢。一个点的话好像也可以哦。
一个点
你看这个是1啊，
对对对，
这个是1，这个是0，这是1加1也是2，一个点也可以，2个点也可以。
那应该差不多。
然后你就慢慢增加。来谁？
这没有上过整。
那边上到分，在哪里？10分。我就说，等下我看一下啊。有上到分哎，9A1哦，9A1我给你，诶，我怎么给你4分呢？哎，我给你
是2来的，
2是错了，2是错了，
我不要看了。
2是错了。你9有没有其他地方？你9就一个地方了。
我不懂。
这个是可能是我前几个改了，忘记改掉。
不要看了。
你9确定没有地方了？
直接撤回来。
没有地方了？
再看下去就出来。
有没有地方了呢？
不懂。
啊什么？你记得答案你不懂？是啊，我就看到有时候忽然间又跑一分出来。
真的是考试写出来。
你分在如果以前是不同的题，什么意思？一张
来。
Then I did another.
You did it.
Yeah.
What do you do?
And then I also did another tautology truth table.
Can you like say your name? What do you do? What do you do? It was fun. I thought you want to do
Yeah, this one.
this one.
So we have to prove it. So I turned it into if it was a false statement, right? So I negated the whole thing, and then I don't know how to explain it.
Yeah, I understand what you say. You just keep going.
Yeah, I negated it, and then I just kept breaking it down afterwards to prove that it's not gonna. It's gonna be the same results either way, because it's all true. Yeah.
No, I mean you. No, the problem now is what's the relation between these two? What's the relation between these two?
They all work out either way the same. They're all the same.
Okay, show me. What? I thought you already done. Yeah. So
Like
if you so how can I? So if you can't explain, how can I? know whether you understood or not. Right?
I'm just bad at explaining, but like,
What?
struggling through.
I know you are struggling, but I can give you mark. Not that I don't want to give you mark, but you need to me then you get what I mean? You don't need to like how to say. I mean, bye
Bye bye.
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 I can give you mark. I definitely can give you mark. You don't need to be nervous. I can give you mark. You just need to tell me why these two are the same. That's all.
I just don't know how to say it. in
If you
words.
don't know, then if you can't say a word, you write down. Like if you can't tell how I okay. Imagine you are the teacher. You just imagine yourself. You
Oh
put
my.
yours. You can full mark. You give this student full mark. You're willing to give this student full mark.
Table and I did this, like, but I don't know how to say it in words. Just think of me as a shy student, like.
No,
Like,
I mean
me,
you can be shy, but I mean
you have a heart.
no, I definitely got a heart, but
On in.
I can't.
Or
How to say?
just your heart.
It's not about heart or it's about.
You know what?
It's like how to say? Can you understand me or not? Can you understand me? Can you understand me or
I'm
not?
choosing not to.
Now you see, you don't want to understand me, and then you want me to understand you. So how should we have a mutual understanding? Right? Yeah. You try to understand me first. I understand you now, so I give you chance. I didn't say I cannot give you. I don't say that.
Do I have to prove again? Like,
No. Do you know what you want to do first? What do you want to do?
need to prove that this is a tautology.
Okay.
using the breakdown method with the commutative
breakdown
associated geometry.
Okay, sure, good, good, nice.
And then
Uh-huh.
I tried negating it.
Okay.
And then I tried negating
Yeah,
it, and then I broke it down. I broke it down, and
Sure.
yeah, as you can see right over here. And in the end, it just proved that either way, whether it's negated or not, it just each of the smaller, when it's broken down, it just returned back to the original. Back to the equation. If P, then Q and R and stuff.
You see here, you see here. So why suddenly this long stuff become the short stuff?
I broke it down. That's the
How?
one.
How?
For example, I cut it from like here. I cut it there, and it's the one we took in class.
I mean, how? I can't see how. I can't see. Oh, you're mixing a lot of stuff together. So that's wrong.
It's not wrong.
You see, what you are using here is you implies Q and then you go to P, right? Is this what you are using?
No.
I mean P and Q and then you stop with P. So why suddenly there's these two things here?
I wasn't going in order.
Suddenly going here. Well, I just asking you where's this part go? Why suddenly disappear?
No, I cut it.
Why you cut it? Why can you cut it? Why just cut as you like?
No, because because I was cutting from the and part, the
I know.
negated part.
Yeah. So why you cut it? So how can you cut it?
Because this is combining them both. So I want it to be like if we not combined it.
How can you do that? What's that operation?
I don't know how to explain, but like
That's why I said you can't do that. You can't do that. That's a different thing. You can't do that. You can't do that. Okay.
But is it possible to still get it by proving using the J table?
Definitely not. Because my question prohibit that one.
Okay.
I can give you mark if you go back and write down why these two are equivalent.
Okay, I'll do it.
You do it?
Yeah.
That's all?
不是吧
That's all?
Yeah, that's
今天不是吧
Okay, this one.
okay. I'll take
This is
it.
the maximum.
I'll take it.
Make sure you know, please put your exam paper back.
最后一次这个
Thank you.
说服不了就算了吧。
Yeah.
我觉得德巴雷的老师，
About it?
我的 P， 其实我已经有了 P 嘛，
啊，所以我不能够用我有的东西，我就是要用不同的方式来证。
因为有了，因为我们看 P， 我们已经
我知道。
我们有了这个东，我现在看 P 也是这个嘛，我
Yeah.
Part 1我已经有了这个，
Yeah.
就为了证明全部是德句，我现在我 Part C 就做回这个，就证明了它其实它就是还是用来 contrapositive。 因为就是我 Part C 就是用另外一个 contrapositive 了。
OK， 再开一个脑洞。刚才讲你现在讲的东西是不是你说？
就德巴雷而已，其实。
没有不能哦。
因为类似第一题是 P 嘛，我第二题就用 Q 哦，第 C 就是用 Q 就是那个 contrapositive， 那个 Part B 的 contrapositive，
然后
就可以证明到还有这逻辑。
我再讲一个，你再重复。
就类似我现在，看一下那题目，因为我们 Part B 是这样子嘛，
Yeah.
之后我 Part A 其实已经有了这个，这老师说用 Part B to show that this again 嘛，所以我就这样 Part C 做到一个 contrapositive。
这里吗？
不知道。应该是跟
他可以说再见了。
OK， 拜拜。你说这个变成 S， 这个变成 T 是不是？对吧？这个变成 S， 这个变成 T。
就是 Part A 已经了，这个之后 Part
OK。
你为了证明多一点这个，我就用回 Part B 这个 contrapositive 来这个塞进去，就证明它是可的逻辑。
你说把这个变成 S， 这个变成 T 嘛，对不对？是不是这样讲？把这个 S 把这个变成 X， 把这个变成 T， 对吧？
把加个 not 啊，
这整个变成 X， 这整个变成 T 嘛，对不对？对吗？然后你证了 ，OK， 第一步证了，这一个东西是一个 tautology，and then 第二步你证了这个反过来，这个是一个 tautology。但是我问你，这整句话我都没有讲这个东西是个 tautology， 这个是个 tautology。对，
就是因为他们是一样，因为现在你的
OK， 我再把你那个简化一点。你看啊，你讲的是这个 P is the tautology，
对，就是后面对
tautology by part A imply Q is Q 对。
我不行啊。
所以你说我们把 A 证了这个，把 B 证了这个，
你考过也高吗？
不是 C 你证了这个，好，你现在要做吗？
因为我们现在是有了这个，我们Part B是这样子嘛，其实他们两个，其实这个跟这个是一样嘛，因为 我们要 prove 同样的东西嘛，只是我方法不一样了，我就是用 contrapositive 来 prove 它这个是不的逻辑。因为老师你还是 prove 同样的东西是吧？其实要方法不一样嘛。
啊，对，
所以我就用，因为我现在已经有了这个，因为Part B 已经证明了这个 contrapositive 是可以行得通这个 tautology 的，我 Part C 我就用 contrapositive 哦。
我知道，但是现在很乱，你现在很乱，很乱，你现在很
可是
乱。
差不多，这个差不多是，可是其实这个跟这个我其实这个老师要证明那个 P 跟 Q 其实是一样的嘛。
不叫一样。
哎，你 P 这个 P 死的逻辑其实是跟这样子，然后 Q 其实也是证明同样的东西嘛。可是我用 contrapositive 来证明嘛，老师可以明白吗？我怕我的意思传达不到老师那边。
OK， 不然你先告诉我你要做什么先。你要证明这个是 tautology 嘛，对不对？然后周末你去找它的 contrapositive 是一个 tautology。
因为通过这边我们可以发现的哈，
如果你把这个的 contrapositive 证了是 tautology， 为什么证明它的本身是 tautology？
它本身就是我们前面有的。
就是 OK， 我们就一步一步来啊，就是说，
你把，你不是把，
因为我们前面已经有了最前面这个。
if the contrapositive of
contrapositive 什么意思
is tautology，
我忘了。
我都不知道一点。
就是这个 ，then he is a tautology。所以为什么？
记否？
所以为什么？
为什
么？为什么这句话是对的？
我不是忘了。
你在用这个哦。你看，
好像是。
为什么？为什么是对的？这是你在用的东西。